Syntax builds the form we see. Semantics gives it meanings key. Connectives link what minds devise. Quantifiers range through truth and lies. Modus ponens strikes with might. Modus ponens flips the fight. Logic cuts clean, no shallow line. Through the long night, reason shines.
Previously, we discussed what a logical proposition is, along with several examples. Now, let us compare the following two logical propositions. Proposition 1. Golden State Warriors beat the Houston Rockets in Game 7. Proposition 2. If Stephen Curry hits at least 6 three-pointers or Draymond Green gets a triple-double and Jimmy Butler is not injured, then Golden State Warriors beat the Houston Rockets in Game 7. The first proposition expresses a single, complete idea and cannot be broken down into simpler components, much like an indivisible atom. We call this an atomic proposition. The second proposition, however, is made up of several simpler propositions connected by logical connectives. These simpler propositions act like atoms joined by chemical bonds to form a molecule. We call this a compound proposition. The basic logical connectives include the negation, not, the conjunction, and the disjunction, or the implication, if, then, and the equivalence, if and only if. The following example illustrates how to use connectives to build compound statements from simpler ones. Let P be the proposition, mathematics is the queen of the sciences, and Q be the proposition, number theory is the queen of mathematics. Then, not P. Mathematics is not the queen of the sciences. P and Q. Mathematics is the queen of the sciences, and number theory is the queen of mathematics. P or Q. Mathematics is the queen of the sciences, or number theory is the queen of mathematics. P implies Q. If mathematics is the queen of the sciences, then number theory is the queen of mathematics. P is equivalent to Q. Mathematics is the queen of the sciences, if and only if number theory is the queen of mathematics. A compound statement may contain one or more of these connectives. In cases where more than one connective is involved in a compound mathematical statement, their order of precedence is as follows, from highest to lowest: negation, conjunction, disjunction, implication, and equivalence. If we wish to emphasize a different order of operations than this natural hierarchy, we use parentheses. For example, consider the following two compound propositions. The first should be interpreted as not P and Q together imply R. However, the second should be interpreted as not P and Q implies R. Each compound proposition can be associated with a graph, called its syntax tree. A syntax tree visually represents how a compound logical proposition is constructed from its atomic components using logical connectives. The leaves of the tree stand for atomic propositions, while the internal nodes represent connectives. The simplest examples of syntax trees, each corresponding to one of the 5 basic logical connectives introduced, are given below. As we will see, this hierarchical structure clarifies the order of operations and the scope of each connective, making it easier to understand how complex propositions are assembled step by step from its simpler parts. Now, with all the groundwork laid, let us revisit the compound proposition introduced at the beginning and see if we can better understand its structure. First, we identify all the atomic components. Proposition P. Stephen Curry hits at least 6 three-pointers. Proposition Q. Draymond Green gets a triple-double. Proposition R. Jimmy Butler is injured. Proposition S. The Golden State Warriors beat the Houston Rockets in Game 7. The outermost scope is the implication, with the consequence being the Warriors beating the Rockets, and the premise being a conjunction. This conjunction consists of 2 parts. The first is a disjunction between Curry and Green's performances, and the second is a negation indicating that Butler is not injured. As a result, the full compound proposition is achieved. Congratulations! You now understand how to read and write compound propositions. However, we have not yet addressed how to determine their truth values. An important tool for this is the truth table, which we will introduce in the next section.
信了，ten say。